This video will cover how to construct a hypothetical binary phase diagram based on given instructions. Similar to constructing hypothetical one-component phase diagrams, constructing binary phase diagrams is a great way to familiarize yourself with the binary systems. This part of the course has only one learning outcome. After going through this lecture and the given exercises, you should be able to construct a hypothetical binary phase diagram based on given instructions. Furthermore, these instructions will use the nomenclature that we have introduced in previous lectures. The best way to illustrate the construction of hypothetical binary phase diagrams is via examples, and therefore we'll revolve this lecture around a problem that we'll solve. Our example concerns the following hypothetical binary A-B system. In order to construct this A-B system, we have 7 different conditions that the phase diagram should comply with. The first one is that component A melts at 1850 degrees Celsius, and the second one is that component B melts at 1700 degrees Celsius. Third one, there's an intermediate compound, A4B, that melts incongruently at 1500 degrees Celsius. There's another intermediate compound, AB, which melts congruently at 1600 degrees Celsius. We also have a compound, AB3, that is stable between 1200 and 1350 degrees Celsius. Furthermore, there's a eutectic that is formed between A4B and AB at 1400 degrees Celsius, and there's a eutectic that is formed between AB and B at 1450 degrees Celsius. We'll start off by drawing the x-axis and y-axis, defining the temperature and composition interval. As always, we draw the temperature on the y-axis and the composition on the x-axis. And in this case, I've chosen mole percent of B as the composition on the x-axis. I chose the mole percent as we have stoichiometric intermediate compounds that we don't know the molar weight of. Thus, the compound AB, it will be placed here at 50% B. It doesn't matter if we use mole percent of A or of B. It will be the same information contained in the diagram. I chose to use the temperature interval between 1000 degrees and 1900 degrees Celsius. The important thing is that you cover all information given in the instructions. I could just as well have drawn the y-axis between 1150 degrees Celsius and 1850 degrees Celsius, as this would include this lower temperature and this highest temperature in the diagram. So now that we have defined our space, we can start to add the information given in the instructions. The first two conditions given are simple to add to the diagram. Component A melts at 1850 degrees Celsius, so at 0% B, we put in 1850 degrees Celsius. And component B melts at 1700, so at 100% B, we put in 1700 degrees Celsius. The third condition says that we have an intermediate compound, A4B, that melts incongruently at 1500 degrees Celsius. First, the stoichiometry of A4B says that we have 20 mole percent B, that is here. Second, the criterion says that this compound melts incongruently at 1500 degrees Celsius. It doesn't say anything about the compound decomposing at temperatures lower than this. Therefore, we can draw the line from the lowest part of the diagram, which in this case is 1000 degrees Celsius, up to 1500 where it melts. As of right now, we'll not concern ourselves with this intermediate compound melts incongruently. Instead, we'll move on to the next condition. The fourth condition says that the intermediate compound AB melts congruently at 1600 degrees Celsius. This compound contains 50 mole percent B. Furthermore, the compound doesn't decompose, and we can therefore draw the line at 50% for the lowest point in the diagram, 1000 degrees Celsius, up to the melting point, which is 1600 degrees Celsius. Just as for the previous compound, we'll not concern ourselves with the fact that this intermediate compound melts congruently. Instead, we'll come back to this later. The final intermediate compound, AB3, does not have a melting point. We start by marking out the composition of this compound in the figure. I've drawn this dashed line across the whole temperature interval to mark this composition, which is 75 mole percent B. And you can get this 75 mole percent from the stoichiometry of the compound. Based on the instructions, we can add the lower and upper temperature stability region of this intermediate compound. Now we have a field between 1200 degrees Celsius and 1350 degrees Celsius. In this field, we can solidify the dashed line, marking the stoichiometry of the compound. We'll also remove the remainder of the dashed line. The sixth condition reads that a eutectic is formed between A4B and AB at 1400 degrees Celsius. Therefore, we can draw this line between A4B and AB at 1400 degrees Celsius. We know that we have no liquid under this line, but we will not concern ourselves with the liquidus line just yet. Instead, we move on to the final condition. This final condition says that a eutectic is formed between AB and B at 1450 degrees Celsius. Therefore, we can draw this line between AB and B at 1450 degrees Celsius. Again, we know that below this it's only solid, but we will not draw the liquidus lines just yet. Now we have some sort of skeleton for the hypothetical binary phase diagram. But there's one more line that we can draw before starting to add a liquidus curve. And for this purpose, we move back to the third condition. The third condition said that compound A4B melts incongruently. If you remember from the previous lecture, this means that the pure intermediate compound A4B will not form a melt of the same composition as A4B just above the melting temperature. This means that we have a peritectic reaction at 1500 degrees Celsius, as marked by this one, and therefore we also draw this line slightly to the right of the composition of A4B. As this is a hypothetical diagram, we don't know how far to draw this one, so we do it arbitrarily. So now we have the complete structure of the hypothetical phase diagram, and we can start to draw the liquidus lines. By the leftmost line, we can draw an arc from the melting point of A to the peritectic point of the incongruent melting compound A4B as such. In the next step, we consider conditions 4 and 6 together. Condition 4 said that compound AB melts congruently at 1600 degrees Celsius, and condition 6 said that a eutectic is formed between A4B and AB at 1400 degrees Celsius. And therefore, we can draw this typical liquid surface representing the eutectic that is formed here. Now, I have drawn this eutectic arbitrarily because we didn't get any instructions on at which composition it should occur. In order to complete the liquidus line, we consider that the melting point of B is at 1700 degrees Celsius, that AB melts congruently, and that this eutectic between AB and B is formed at 1450 degrees Celsius. Based on this, we can draw this typical surface of the liquidus line in connection to the eutectic. And again, we didn't get any information on where the eutectic should be, so I draw it arbitrarily. I could just as well have drawn it right here or right here, and it would satisfy these conditions. This is actually all the information that was given in the instructions, and we have successfully drawn the hypothetical phase diagram that complies with all the specified conditions. In order to make it complete, we should add the labels to all of the fields. The liquidus is marked by an L above the liquid surface, which we can see here. And if we would have a part of liquid immiscibility, for example here, we would denote it as L1 plus L2. We can also add a field of A plus L right here, because here we have 100% A. And as you remember, this one right here was A4B, and therefore we can add A plus A4B here. And in that case, we can also add A4B plus L right here, because this is A4B, and on the other side you have L. And as you remember also, this is representing AB, and we can therefore add A4B plus AB in this field right here, and then you can add liquid plus AB here, and also AB plus liquid here. And we also know that this rightmost 100% B should be only B, of course, so therefore we add L and B here, and on top of this one, we see that we have AB plus B, and that's because this line represents AB and the rightmost axis here represents B. Furthermore, we can add the same down here because this is just a decomposition reaction if you heat it in this composition. The last compound to be added is the AB3, which represents this line. So therefore, in this field, we have AB plus AB3, and in this one, we have AB3 plus B. So this diagram is now complete, and it contains all the information. One thing that you can consider regarding this example is, where did this data come from? Well, of course, this diagram is purely hypothetical, so it was completely made up. But you can still see that this is how a typical binary phase diagram can look like. We might actually just as well have been given instructions for a real system, for example, the CaO-MgO system. In this case, we would have been given data for melting of pure CaO and pure MgO, as well as other data for that specific system. There are actually methods to determine such data, as well as methods to derive the shape of the liquidus curve and methods to build databases that can be used to calculate phase diagrams. This is something that we will go through in the lecture called Determination of Phase Diagrams. But as for now, we continue with how we construct diagrams if we have partial solid solutions. Many of the binary systems have partial solid solutions where a solute A is soluble to some degree in solvent B or vice versa. To illustrate how to draw these type of hypothetical diagrams, we'll consider a diagram where B in A forms a partial solid solution labeled alpha, and A in B forms a partial solid solution named beta. Taking the alpha phase as an example, you see that we have two possible ways of drawing this phase. In the upper figure, the metastable extension goes into the two-phase region. So the metastable extension of this line goes into this two-phase region, and in this one, the metastable extension goes into the two-phase region of alpha plus beta. In the lower figure, the metastable extension of this line goes into the single-phase region of alpha, and the same goes for this line. So we ask ourselves, which one is correct? The answer is that the upper figure is correct. The follow-up question is, why should it be constructed like the upper figure? And in order to answer this, we have to consult Gibbs free energy curve of each phase. Consider the upper version of this phase diagram with alpha and beta. It changes to alpha and gamma in this phase diagram, but the principle is essentially the same. And I refer to this as the left diagram, which you might suspect we will also have a right diagram soon. So in this figure, we've added the function also of the Gibbs free energy of the solid solution phases, the alpha phase and the gamma phase. And these are given at a fixed temperature T. You can see that this temperature is marked by the dashed line in the phase diagram as well. The Gibbs free energy function of both the alpha and gamma phase have some sort of parabolic appearance with change in composition. And in the figure, there's also a tangent drawn at composition G and at composition H. And you can see that this tangent appears to be shared by these two phases. In the lecture called Determination of Phase Diagrams, we'll use the chemical potential to show that this shared tangent represents the equilibrium between these two phases. But as of right now, we'll be satisfied with knowing this information, and we start by connecting the lower figure to the upper one. In the upper figure, between composition G and H, a mix of alpha and gamma provides the lowest overall free energy, and therefore represents the equilibrium composition. Going down via the projection to the lower figure, we can see that the tangent represents the Gibbs free energy at a combination of alpha of composition G and gamma of composition H. So, for example, we mix this with this, and we will be along this line, which has the lowest overall Gibbs free energy. On the left side of G, we don't have a shared tangent between the alpha phase and gamma phase, and therefore these two cannot be in equilibrium. Therefore, the alpha phase has the lowest overall Gibbs free energy in this region, and we only have alpha available right here. The same applies on the right side of H, where gamma is stable. So far, so good. We haven't proved why the metastable extension should go into this region, but we have introduced the concept of coupling this Gibbs free energy functions to the phase diagram. So let's move on to this infamous right figure right here. In this figure, we have chosen a different temperature for the Gibbs free energy functions, and it's also placed on top of the diagram now. And the temperature chosen is this one, represented by this dashed line here. Similarly to the previous case, we'll connect the free energies to the phase diagram. Perhaps the simplest case is the composition between C and D, where there's only liquid. And it is quite clear because the lowest overall Gibbs free energy of the system will be that of the pure liquid phase here. Between 100% A and composition marked lowercase a, we have the solid solution alpha, and we don't have any shared tangent. That is, we only have alpha. So that is this one, 100% A to A. This is the lowest overall free Gibbs energy of the system. Similarly, if we go between 100% C and F, which is here, 100% C and F, this one will represent the lowest overall Gibbs free energy of the system, and we will only have the gamma phase. So gamma phase at this temperature right here. Between A and C, that is right here, A and C, you can see that they have a shared tangent, so they are in equilibrium, and the lowest overall Gibbs free energy will be a combination of the liquid with composition at C and the alpha phase with composition at A. And that is also something that we can see here. We are in this two-phase region here. Similarly, between D and F, we have gamma and liquid, which we can see that the gamma phase is here, the liquid phase is here. D and F, they have a shared tangent, and the lowest overall Gibbs free energy of the system is a combination of the liquid of composition D and the gamma phase of composition F. And that is something that we can relate to this phase diagram right here. And now finally, we arrive at what we were supposed to show. Between B and E, we will find the metastable extension. So B right here and E right here, or in the figure. So in this case, we disregard the liquid phase and we draw a shared tangent between the alpha phase and the gamma phase. So this shared tangent, if you take it at temperature T and composition B here, for example, we will see that this metastable extension of this phase has to be in this two-phase region. And this was actually all that we were supposed to go through this lecture. We showed how to draw a hypothetical binary phase diagram, and we also shown how to take into account if we should draw solid solution in hypothetical binary phase diagrams. So the last point, we found that the metastable extension should always go into the two-phase region. So let's finalize this lecture by reviewing the learning outcomes. After this lecture and working with the exercises, you should be able to construct a hypothetical binary phase diagram based on instructions. And these instructions will utilize the nomenclature that you apply in phase diagrams. In the book, there are two exercises, 5.1 and 5.2, and I recommend you solve both. The first one has a solid solution phase, or several of them, and the second one has a lot of intermediates and congruent and incongruently melting compounds. If you have any questions, you can come by my office at any time, or you can email me and we could go through some of the concepts more thoroughly in class. So thank you for listening.